So what is due on Monday? The packet. Specifically, though, hold on, you had 2 packets, so which one? Wait, why is this so weird? Oh, there we go. That's more normal. Sorry, guys. I got totally thrown off. The worksheet one is due on Monday. So I have you guys having out the notes one because we're going to do a couple more examples. And if you guys have any specific examples you want to see from the notes one, we'll look at that just in case someone's already thought ahead about the worksheet. But first of all, we did not get to spend a lot of time yesterday on section 5.1, the slope field. So I do have your homework behind the packet ready to go if you guys do have any questions. So let's start really quickly on the odds, because those are the ones that you came into class yesterday being like, I don't know what's going on. Do we have any odds that you know right now you would like to talk about on section 5.1? If so, throw that hand up as quick as possible. Any odds? Wow. All right, any evens? You were supposed to use the video from yesterday to check, to grade. Some of the directions were weird. Yeah, Ale. 30? 30 was a little weird, just coming back to the book really quickly, because number 30, the direction said find a particular solution, which in the past has meant we have to go looking from the differential equation backwards. But if you watch the video on number 29, or if you were looking at maybe like a calc chat on number 29, trying to get a feel for number 30, you would have seen that actually they already gave you the general solution. You didn't have to go looking for it. You didn't have to go backwards by yourself. They gave it to you. And so can anyone give me a quick recap as to what they actually wanted you to do? They gave you the general solution to the differential equation. And what's this guy down here? Yeah, it's a clue. What do we always do with clues? Save them until later, but now's the later. This is the weird one. There was nothing to do except for the clue. So just plug it in. Plug it in where? Well, this is a y, not a y prime. This is an x. I see a y spot. I see an x spot. What am I going to solve for? C. So, yeah, literally, I know, right? Like, it was so weird. Usually we have to go looking and solving and doing all this math, but they said, no, it's him. Oh, I mean, we could have tested it and seen that it was him, but it is him. So all we had to do is plug it in, plug it in. So 3 times 1 squared is just going to be 3, plus 2 times 3 squared, that's going to be 2 times 9 is 18. All we needed was C was equal to 21, and then plug it in, plug it in. So in the answer key, what you see is, hey, look, it's 21. I know. It was so easy, it was hard. What else do we have on the evens that you guys need to see? Yeah?
48.
48? Okay, the table. It was more weird directions, right? Yeah, that's why I was totally wanting to go over questions, because what were they asking for in 48? Remember yesterday, at the very beginning of class, it was actually from the end of the day before, I put up these 2 pages where I was like, hey, tricks. Yeah? Oops, sorry, I don't meant to do dual page. There we go. And this one down here, if worse comes to worse, start testing quadrants, testing points. What this little bit of homework was saying is, hey, you can literally plug in points and it should point you to a slope field. That's literally what's going on. So in number 48, you were just supposed to go to this table and say, okay, what if I pick a negative x value kind of far in the second quadrant? So a -4, +2, or a -2, 0, or a 0, 4, or a 2, 4, or a 4, 6, or an 8, 8. They were literally just saying, plug in points, and would that be enough to tell you this is the slope field and not that, not that, not that, not that, not that, not that. Anyway, so they were basically just having you practice plugging in points. And so all you needed to do, for instance, for number 48, was to come up here and say, okay, -4, 2. I mean, you could look at the graph if you wanted, -4-ish, 2-ish. You should see, okay, it should be some sort of positive number. But all we had to do was plug in. So y minus x, 2 minus -4, that's going to be 6. And so then Ali, just keep on plugging and chugging. So we have 0 minus -2, which is 2, 4 minus 0, which is 4, 4 minus 2, 6 minus 4, and 8 minus 8. And all of those, for instance, like 8 minus 8 would have been a 0. Oh, hey, whenever x and y is matched, this would be a 0. I should see little flat lines everywhere the x's and y's. Oh, hey. Yeah, I do. This one follows diagonal lines like we were talking about yesterday. So it didn't ask you to really do any of this work. It was just saying fill in the table, which is why you can see on the answer key. Oh, sorry, wrong one. They just plugged in. That's it. Keep going. Any other evens? 92. He was the one that was like an FRQ kind of, right? Okay. Free response. Number 92 says, consider the differential equation. I'm going to go ahead and take a picture of him just to make life a little bit easier here. Let's see. All right, consider the differential equation 4 minus y times cosine of x. And then it asks us to use him basically for the entire thing. Now, guys, there is one in your worksheet that is kind of a nasty version of this. And even what I told you guys was impossible to solve. I'm going to go put him on this page, and then we can work on the other page. That might be a little bit nicer. There we go. All right. So for number 92, let's see. We have a differential equation. Y is the particular solution. So the antiderivative is possible for us to solve. The initial condition, blue, which is the point 0, 1. Just a few of you get confused as to who's x and who's y still. Portion for the slope field of the differential equation is shown below. So for 0, 1, I can see the tick marks are going by 1s, and if they don't label anything, we always assume it's going by 1s. So 0, 1 is right about there. This one's a little weird, but I see it going up and down, and then down. They don't really have flat ones, which is kind of awkward. But they do have like up slopes and down slopes, and somewhere in between had to be some sort of leveling off. Let me come look in the book and make sure, because that was kind of a nasty picture. 0, 1 is going to go up and then down, seemingly back up again. Then to the left it's going to go down, then up, seemingly back up again. Something similar. It might not be perfectly that, but that's kind of like it. I think it might be actually a little bit weirder as far as like maybe actually going down. But let's see, what else does it say? Write an equation of the tangent line. Ooh, it's making me review last semester. Kiddos, how do we do tangent lines? I'm going to change colors just because I'm not doing the clue anymore. Oh, come on, equation of a tangent line. You didn't forget all your forever cards? What's the line? Y minus. Keep going. Yeah, just do it the easy way. And now, why is Ryan saying y minus f of a? Because he's just kind of saying, okay, f of a could be a y1, and then what could m be? Prime of a, not x, a. And then x minus. Okay, so if you need to, start off with the Algebra 1 version. That's totally fine. But if it's helpful, keep going to the calculus version. Okay, what's my point? Pi 1, right? Okay, so can't I do y minus f of pi equals f prime of pi times x minus pi? Don't I know that when x is pi, didn't they tell me that y was 1 according to the problem? Now who do I need still? F prime. Who's f to take the derivative? I don't have him. Oh, but what do I have? Isn't f prime equal to dy? So can't I do f prime of pi by plugging in, pi, don't I also need my y? There we go. So I can plug in x and I can plug in y, and I get my slope at that point. So it was just a little bit weird, a little bit different. Dy dx is my f prime. Now this one's not in terms of just x would find my f prime of x and y is in terms of both. So I plug in both the pi and the 1. Then all I have to do is simplify a little bit. Y minus 1 is equal to, well, cosine of pi, isn't that a negative 1? 3 times Now, why do they keep going and say, use this equation to approximate? Have we ever done that before? Local linear approximation, tangent line approximation. Where do I plug in 3.2? Right where the x plot is. Why are they asking me to approximate at 3.2? Oh, because it's so close to pi. 3.1415926, 3.2 isn't bad. So I can say, technically according to my local linear approximation, that f of 3.2 is approximately the y value at 3.2. Did we ever use a capital L to be the tangent line? Or is that a BC thing? Did we ever use a capital L? BC thing. Some of you are thinking. We could say y then. Y is equal to. So the f of 3.2 will be approximately the y value. We could say the L value at 3.2, which would be adding 1 to the other side. 1 plus. Well, I guess adding 1. 1's positive, but that guy's still going to be negative. And guys, I don't expect you to be able to do 3.2 minus pi, even though it is the month of March, and March is Pi Day. But we can just box it and be done. Sound good? Any other even questions or odds that you've now remembered that you had that you didn't know a second ago? Slope fields. What kind of questions showed up with slope fields in the homework? Everything from like this weird tangent liney thing, because you're using the differential equation, but match the slope field to the, well, to two different things, right? Either you could be matching slope fields to the follow the flow, the y equals, or you could be matching the slope field to the differential equations, yeah. That's what the AP likes to do the most, is matching. However, they could have you make a slope field, which is why there's so much practice. And ooh, what else makes you practice making slope fields? How about the first page of the packet, cool kids? Right? You have a lot of practice right there. Lots and lots and lots and lots and lots. However, can there be FRQs as well? Yes. Now, the entire FRQ will not be a slope field. Like, a slope field is a great multiple choice question, or a great, like, part A to an FRQ. However, the notes packet does show you what FRQs can look like that involve slope fields. So let's grab out our note packets. We're not going to go through all of them. I just want to show you guys some trends. Remember with integration as net change, I had you looking through all the FRQs, trying to compare and contrast. That would be a great thing to do on your notes packet as well. We're going to do that just a little bit together. But then remember, all that you need to worry about for Monday is finishing up section 5.1, which is matching, a little bit of sketching. Ooh, hey, do you guys see a tangent line come back? Can homework help you on this tangent line approximation, Grace's question that she just asked? Ooh, that's nice. So matching something with a tangent line. Ooh, this looks a little FRQ-ish. Just a warning. This is one of the trickiest types of FRQ because do you guys see this minus? In a colored pen, it might be a good thing for you right now in your worksheet to write, this is impossible for you to integrate. No matter what the question looks like in their A, B, and C, they are not asking you to integrate this. It's impossible. We can match it really easily. There are going to be diagonal parallel slopes. But you cannot, I cannot, integrate this by hand. They are not asking you to integrate. So instead of going from here back to the original, maybe you're going from the original to here. That's a huge hint on this FRQ. Not the entire thing, but one of the parts. You're going to think you're supposed to integrate this. It is impossible to integrate an x plus y or a y minus x or an x minus y. It's impossible to integrate that at our level. So they will not be asking you to go from dy dx back to y, but you might need to go from y to dy dx to make it match. Anyway, you have some more matching over here, and then you have some more matching back there. So there were a couple FRQs. Let's peek at your notes packet and say, okay, we did this, we did some sketching, we did some matching, we did some more matching. Okay, we didn't really do much from number 11 on, right? So let's check out what number 11 is. Number 11 gives us a differential equation No plus or minus, which means maybe we could actually anti-derive. It has us sketching a slope field, but that's just part A. Then part B is talking about, oh guys, look. It's talking about a what? A tangent line, and using a tangent line. It's like the homework problem that Grace just asked. Letter C says, find the particular solution. Hey, what was going on in homework when they were asking you to find the particular solution? No? Nobody asked one today, so I thought you guys totally got it. I have one right up here. I think it was the e to the xy one. There's an even with an e to the x, something, 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 something. Here it is. They were asking you to go backwards. What were they asking you to do? Integrate. And when you integrate, you get a plus c. And what's going on in this guy when it says find a particular solution, but it also gives you a point? Are you going to have a plus c at the end? No, you're going to have a number. And then it says, okay, this one you're using a tangent line. This one you're actually solving and plugging in. And this one you're comparing. Okay, that kind of looks like homework. Number 12. Do you see how this is an actual FRQ? It was number 5, so it was non-calculator. They give you a differential equation. Look at that plus. It would have been impossible for you to integrate. They could not possibly be asking you to do this. Once again, if there's ever a plus or minus with x's and y's. But you could make a slope field out of it. Ooh, this is interesting. What are they having you do? Find the second derivative. But guys, how do we take a derivative if we have x's and y's? Do you remember implicit differentiation from last semester? What would be the derivative of 1/2 x? Just 1/2, right? What would be the derivative of y? 1 dy dx. And then what would be the derivative of minus 1? 0. So this one would be a little bit interesting. Just a little bit. Because when you go to take the derivative for letter B, you would get the second derivative equals 1/2 plus dy dx. Wait a minute, but don't they want you to, in letter B, describe the region in which all the solution curves are concave up? Wait a minute, what does concave up have to do with the, what does concave up have to do with my second derivative, guys? The second derivative is going to be positive, right? So I need this guy to be positive. But they said describe the region in the xy plane. I don't even have y's. I don't even have x's. Hold on. What do I do if I have a dy dx show up again? Plug it in, plug it in. So whenever they say something like describe the region, what they mean is you're not going to be able to give me like a point. You're going to give me a relationship of points. So all you really would have needed to do is plug in 1/2 plus 1/2 x plus y minus 1 greater than 0. Basically, get y by itself with a greater than and move everything else to the other side. That's all it's saying. Describe the region. Be like, oh, okay, well, as long as y is greater than, move everything over. Sorry, there you go. Move everything over and then you have it. That's a little weird thing that does show up in slope field type questions, especially with impossible to solve differential equations. If it's impossible to integrate, they're going to make you use it some other way. Maybe concavity, second derivatives, or maybe some sort of weird, look at letter C. This is a lot like your worksheet, the one I just showed you that was impossible to solve. Doesn't letter C make you think that you should solve the differential equation? Doesn't this look like you're going backwards? How can they be particular solution? Does it say find the particular solution? No. But a lot of kids would read this and be like, oh, I better integrate, and then they would do something horribly illegal and they would go down this rabbit hole and waste all this time on a question that wasn't even being asked. This one says, oh, there's an initial condition, f of 0 equals 1. And it says, does f have a relative min, a relative max, or neither at 0? Do you think this is something where you would need to actually think about what the derivative is at 0, 1? Maybe it's going to be 0, maybe it's going to be dne, which means it's a possible extrema. And then, do you think we could look at the second derivative at 0, 1? Because we will have just found that. Guys, is there a test that says if it's a critical number and the concavity is, we can say whether or not it's a min or a max? I think you should think about the second derivative test. But I want to show you, in this FRQ, they never actually asked for you to integrate. You have to somehow put all the clues together and figure out how to analyze, how to answer, how to think about a particular solution without actually finding it, because once again, plus or minus impossible to integrate. We can talk more about that on Monday with the worksheet one, if you guys tackle that one and get stuck. What else do we have? We have a few more, and we're not going to necessarily cover all of them, but number 13, we're just trying to compare and contrast, yeah? Number 13, you would sketch a slope field. Letter B, you would follow the flow, right? You would follow the flow. Letter C, particular solution. What does it say this time? Find. Oh, so that means integrate, right? So if they say find the particular solution, that is integrating, which means it must be possible. Guys, look at that differential equation. Is there a plus or minus? No, so it is possible to find. So this one you would actually be integrating the dy and then whatever you have on the other side with the dx, you would be integrating on that one. Sketch another solution curve. Look at them being snazzy. Oh, and then they say find another one. You were supposed to do this twice. What was different between C and E? They both say find. Isn't it the exact same answer? Different initial points. So what's going to change, the equation or the C? Yeah, just the C is going to change when you go plugging in. Yeah? Look at example 14. Letter A, sketch a slope field. Letter B, follow the flow. Letter C, find. So what are you going to be doing? Integrating. And it says part B, so that means there's a clue. So is it going to have a plus C or is it going to have a number eventually? Ooh, look at part D. What did they bring in? Yeah. How do we find the second derivative with the first derivative? Derive it. Do you even need to worry about weird dy dx's in this one, or is it just going to be normal? Nice. You don't even have to worry about implicit, but sometimes you do. And since they're having you talk about the second derivative, what else are they going to ask you about? Concavity. Oops, that is not a straight line, but you guys know what I was talking about. Sorry, concave up, concave down. That would be some sort of sign chart, right? Trying to think about what's going on. A sign chart for the second derivative. Are we seeing trends like what they ask on slope field type FRQs? Tangent lines, concavity, but then otherwise you're sketching or you're integrating or you're doing something weird like the worksheet about a clue when you can't integrate. Okay, let's look at the last two. I think it's the last two, right? Yeah. Example 15. They give you a differential equation. Letter A says slope. Oh, sorry, slope. Graph the slope field. Sketch it. Letter B says use it to explain why a solution could not have. Could not have, does that mean this must not follow the flow? Okay, you're just going to be talking about the flow and the tangent lines and how this doesn't match up with what the tangent lines say. What's letter C say? Find. So what are you doing? Integrating. Clue, finding C. Range. Ugh. Range. Oh, doesn't that have to do something about y's? Okay, let's take a second about this, just real fast. Okay? This is like a homework problem. I like this one because this one's new and it's unique. Homework problem. If we needed to find the particular solution, I know I'm writing it down here. Do you guys see why I am dividing the y minus 1 squared and moving the dx to the other side? Do you see what I just did? Why couldn't I leave the y's on this side? Why not just multiply by dx and then integrate? Is it legal to have this guy here? No. However, who's on the other side just waiting for this? The dy. So if I just rearrange a little bit, is it legal to integrate something with y's and dy? And integrate something with x's dx? We're going to actually come back to this guy because we actually haven't talked about this. This is called separation of variables. It's when our differential equations get a little bit messier, because in homework you guys should have only seen expressions of x, and all you had to do was multiply dx on the other side and integrate, and this side was always a 1y. But in this case, it would not be a 1y. It's way harder. Look at all this stuff. So we'd have to actually integrate the left side and integrate the right side and see what happens. We're going to be doing that today in section 5.2 a little bit, just with one very specific type. And then in section 5.3, we're going to see nasty ones like this. So we'll come back to this one once we get there, especially that range question. I want to get back to that. But for right now, we haven't quite gotten to this level of difficulty differential equations, so we'll wait. Last but not least, example 16. Look at that differential equation. Can they be asking you to actually integrate? No, it's impossible. Okay, well, letter A says, oh, look, they did it for me. That's nice. So wouldn't you have just followed the flow through 0, 1? Would you guys have done something where it goes swoop down? And then maybe like a swoop over? And then 0, negative 1, swoop down-ish, right? And then swoop over-ish? Does that look okay to you guys? Check out letter B. Why is this one so nasty? Didn't we just say it was impossible to integrate this? But what does the wording say in letter B? Do you see it? Why does that mean? What do we always do when it says find a solution to a differential equation? We integrate, but what did I just tell you? So pause and look. They gave you something that makes it possible. You are not able to go from here to here. So if you can't go that direction, maybe we should try to work backwards? How can we work backwards? We can't integrate dy dx to get to y, but can we derive y to get to dy dx? Okay, so letter B. What happens if we take the derivative of what they told me was the particular solution? Do you guys see what I'm doing? We can't integrate to go this direction, so let's try the other direction. What happens if you derive y? You get dy dx, right? Oh, wait. We know what this is. It's 2x plus b. Sorry, guys. 2x plus b, right? Not mx plus b. Okay. So what's the derivative of 2x plus any b, any constant? 2. Oh, well, that has to match up with 2y minus 4x, right, guys? Because it has to match up with this guy. Find the value of b for which this is a solution. Can I solve for, I don't know, think substitution. Can I solve for something like maybe, I don't know, for y? What happens if we solve for y? Yeah, I could add the 4x to the other side. I could divide everything by 2. I would get 4x plus 2 all over 2, which y equals 2x plus 1. Oh. What do you guys see? What does b have to equal? 1. Now you could just compare these two, or you could say, well, if that's true of y, I could go ahead and do a substitution with the y right there. And I could say, okay, so if y has to equal 2x plus b and y equals 2x minus 1, you could go ahead and plug and chug. So y equals 2x plus 1, which has to equal 2x plus b, but at the end of the day, you get b is equal to 1. Justify your answer. Why? Well, the derivative of this particular solution has to match up with dy dx is 2y minus 4x, and the only way that's possible is if b equals 1. Dun, 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 dun. Did I integrate? No, there was another way. So if nothing else from today, there's been multiple years that I've had kids be like, they gave us an impossible differential equation and said find. They might say find to an impossible to integrate differential equation, but do they mean take the integral? No, there's always another way. Does that make sense? And that's going to be helpful on the worksheet for sure. If you guys look at letter C, it talks about local extrema again. local max, local min, and I would point to you one more time. You're going to need to think about critical numbers. Does dy dx equal 0 or dne? And what is the second derivative? If you're doing a slope field, you're always thinking about critical numbers and the second derivative test for relative extrema. That's a quick note that you can make in a colored pen as well. Kiddos, we'll get back to this worksheet when we get to section 5.3 to talk about harder differential equations, but for right now, let's go to 5.2. We're working our way up to being able to integrate harder differential equations. Slope fields just said, like, hey, there's another way to deal with them. We can visualize them without actually solving them. But 5.2 says, okay, let's start off with a very, very particular, harder type of differential equation called exponential growth and decay. And then section 5.3 said, let's talk about all the ones that are possible to solve by hand, which means the ones without addition and subtraction of x's and y's. So here we go, section 5.2. Oh, I guess I had all the FRQs we could have looked at there. Oh, well. Thanks, guys, for letting me just sit and look at them over here. That finished for Monday. Come with questions. Let's go ahead and zoom in on this page. Okay, once again, really quickly. Oh, I just closed that. In homework last night, were you guys, or I guess 2 nights ago for most of you, were you solving for any integrals? The one that we just went over questions in the book a second ago. You were integrating stuff, right? Donde? Here. But what was true about every single one that they asked you to find the general solution for? Every single one. Look at it. Only in terms of x and 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 x. Now, were all of them easy? No. Did I make you do all of it? No. Did I give you a hard one where you had to do a u sub? Maybe not ridiculously hard. I could have made it e to the 2x and made it an arctangent with e. That'd be fun. But I didn't. It was just a u sub. I think it was ln of at the end, something like that, right? But all of these were just in terms of x. And then we were just looking at the slope field note packet. And I started showing you FRQs that suddenly got a bit harder. Why? X and y multiplied. Why? Oh, that one's impossible to integrate, right? And then we kept going. X over y. And then we kept going. Oh, that one's only in terms of x. That one's nice, little baby u sub. That one's not bad. And then x times, and then, okay, so section 5.1 was keeping it basic. Section 5.2, do you see how we're starting to branch out? So here we go. Solve the differential equation for y. I was telling you guys in 5.1 that big old idea that we talked about, how, in general, the antiderivative of an f of x dx is equal to, and I said we've been writing this, but it's because we've only been seeing the most basic antiderivatives where there is a plus c. That's always the case, and let me show you why. You ready? Solve the differential equation. We would have to take y prime, and we would have to make y prime dy dx. And when we make dy dx equal to this differential equation, remember section 5.2 is one very specific harder type of differential equation. It's not all of them possible. You're going to see ones that have division with x's and y's alone. If we were to do what you did in homework, section 5.1, which hopefully you did, multiply dx to the other side, it would be illegal to put an integral right now. Because we can only integrate, that's illegal. We can only integrate if we have a function of, just like u sub, we have to have it all in terms of x. So who does not belong? So technically, when we multiplied the dx, we should have also multiplied the y. So we should have multiplied the y on the other side to get y dy and the dx as well. So we're moving the dx over and we were moving the y over. Now it's completely legal to integrate. Doesn't mean it's easy. Well, it's not too hard, is it? This one would just be x squared plus c. This one would be 1/2, oops, 1/2, oh dear, 1/2 y squared. And it could be plus his own c, but remember, I could have a c1 here and a c2 there and subtract, and they absorb each other. Totally legal. However, when we're solving differential equation for y, we want to get y equals f of x by itself. So is y by itself right now? No. Keep going. There's an extra step that you guys didn't need to worry about in 5.1 because it was the y alone already. So we'd have to multiply both sides by 2. And after we multiply both sides by 2, what would we have to do? Square root it. But when we square root, something funny happens. So we end up with the absolute value of y is equal to the square root of, the 2 could stay on the outside or you could come on the inside. It could be 2x squared. 2 times c could be a new c. But can I write this with a plus c on the outside? Is it legal in any way, shape, or form to randomly just put the plus c outside the square root? No. So the more complicated the differential equations become, the more entrenched c becomes as well. Sometimes c is going to get stuck in a way that he cannot just be added on the end like the basic ones that we've been seeing. And it's totally fine. It's totally legal. Technically, some of you are like, why'd you do absolute value? Well, it's back from Algebra 1. The square root of any squared is always going to be an absolute value. Just you say something like absolute value equations, we just go to a plus and a minus. So you could do plus or minus square root as well. We'll just leave it there for now. But this is an example of a harder differential equation whose integral wasn't really that bad, but we saw how c got stuck. However, that's not the special one for section 5.1. These ones are. That's not the special one for section 5.1. These ones are that you already wrote. Directly proportional rates of growth. The rate of y is directly proportional to the actual amount of y. And the rate of y is, I want to say inversely proportional. But technically, they're both a directly proportional relationship. You guys probably don't remember tons about directly versus inversely. I know that you've heard it multiple times in Algebra 2 and in maybe geometry and in pre-cal for sure. But it just means there's a constant k times y. You're going to have to deal with that just a little bit. But with both of these, whether it's a positive or whether it's a negative, they're both directly proportional technically. But what ends up happening is a little bit different. These ones all have to do with growth and decay, which, ooh, that's a chemistry thing, right? Like radioactive elements growing and decaying. Carbon-14, that decays at a very, very slow rate. Interesting. Doubling half-life, ooh. Anyway, yeah, you guys aren't in AP Chem. It won't be as exciting for you. But coming back, we're going to be dealing with not x, but time. Time is x, okay? But if I was to do what I did was to multiply by dt, because I can't take an integral as it is right now, and each of these multiply by dt, would I be good to start integrating right now? No, because who's stuck that I don't want there? So I'm going to go ahead. He's not allowed to stay. Now you might divide by the k2, but if you realize we want the y by itself, let's just leave as much as we can over here. So I'm going to do that on both sides. So what we end up with is y is equal to the integral of k dt. And this one will be very, very similar, just with a negative k instead. I'm going to go ahead and put this one in parentheses, because we're not going to actually solve that whole one out, because it's going to be just like this one, but with a negative instead. If we were to integrate this side, it's actually not that bad. It's just a constant, so I can do k times the variable, which is like x, but it's a t instead, kt plus c. But what's going on the left side with the 1 over y dy, guys? Who is that 1 over y? Yeah, ln. Don't go y to the negative 1. Remember, that's the one that doesn't work. U of y, technically. But if we need to solve for the particular solution, y equals, what do we have to do to both sides? How do we get rid of ln? E. That's how I can get to the absolute value of y equals e to the kt plus c, which you're like, okay, I don't like it, but all right. But I'm about to do something nasty, which actually makes the formula a lot nicer in the end. Because, do you remember something called exponent properties? I'm trying to get rid of my screen. There it is. Whenever we add exponents, isn't it a result of multiplying like bases? So couldn't I technically rewrite it like that? Right? When I add exponents, it came from a multiplication of like bases. This is still a variable expression because I have a variable e to the k is maybe someone I can find, maybe someone I can't. Isn't this just a constant? And just like I did up above with 2 times c being able to be a c, or a plus c1 and a plus c2, and then moving it to the other side and having it be a new c, guess what I do with e to the c? Make it a new c. So I can actually make that a c in front, e to the kt, and I have over here an absolute value of y. Now, if they give us an initial condition, I can actually plug in the y, plug in the t, find a c. I can think about maybe that absolute value once again becoming like a positive or a negative, et cetera, as far as on the other side. So in some ways, shapes, or forms, sometimes I just have us go straight to y equals or y of t equals, and then plus or minus. So you could think of a plus or minus, but then depending on, it'll just be a different constant. So there's another way of thinking about it as well. But this is what we call the exponential growth and decay equation, which might not seem like a big deal to you, but it's used a lot in nature, in sciences, in physics, in chemistry, etc. A lot of things follow or are bound by the natural law of growth and decay. So on Monday, we're going to basically do examples. We're not memorizing a lot in section 5.2 because, long story short, the AP doesn't force you to necessarily be super chem, but we're going to play around with it. Just it's so important in so many different fields. All right, guys, don't forget your AP money. Hopefully, if you don't have it here, you have it by the end of the day. Get it in. If for any reason you can't do it or can't have it, please go talk to the business office or Mrs. Pratt's and beg them for an extra day. Bye, guys. See you later. Business office, yeah. All the way up until 4 o'clock today.